Hi, B2B students from SPC. My name is Chloe. I'm the current B2B math tutor. I just wanted to do kind of a quick recap of my sneak peek of STEM math courses event that I was doing on the dates on the screen. Just kind of going to run through this sort of as a summary of the slides. I believe I did email and post the slides already. Hopefully got those, but this is just kind of explain, why I picked the slides that I chose. So just to get started here, I wanted to first off mention that I am a student at SPC as well. So I'm doing this kind of more peer-to-peer. I have taken pre-calculus algebra and pre-calculus trigonometry at a different college. But then here at SPC, I've taken Calc 1, 2, and 3 with analytic geometry. And then I've also taken differential equations. So just so you kind of know where I'm coming from with the math. And so this whole entire presentation is kind of geared toward getting you to Calc 1. I'm going to take it a little bit farther in the slide, but because you're a STEM major, I'm going to kind of assume that you're most likely going to be taking Calculus 1. Okay, so to get started, just want to mention some resources that I find helpful, and most likely you already know about them. So one is the textbook. I personally find I always buy a textbook to go with my course. I try to, of course, buy the current edition or the one that's recommended. Now, I know sometimes there are free resources available, but I always kind of like to be prepared and just make sure I have something that I can fall back on to use and not just rely purely on my instructor's notes or my own notes, or just winging it with a free resource if the one's not provided that the instructor has. So I definitely highly recommend getting the textbook. And again, if you can't really afford the brand new one that just rolled out for $300 or $400, find a good used one if you can. And if you can't, find a good used edition that's maybe one or two editions old. Definitely math is math, so it really isn't going to matter too much, but I do highly recommend getting a textbook. I also recommend relying on your own notes and homework. That sounds kind of basic, I know, but it really is important with these math classes to kind of have something to look back on and revise and edit your own notes and homework. Don't just write everything that's perfect. Don't erase all your mistakes, just cross them out and then write your corrections beneath if it's stuff that you're not turning in, to your professor. If it's just stuff for you, write your mistakes or correct your own mistakes. That way you can see where you went wrong. Very, very important with math. YouTube is a great resource for math and so forth. Yes, it will take some searching around sometimes, but I'd highly recommend just finding some good, you can find some good professors. You can find some good quick tutorials. Just something to get the notation down. Sometimes you're like, man, I know this stuff, but I'm just not following this. Sometimes you can find some great tips on YouTube. I also recommend a few graphing utilities that are free online. Their website's Desmos. You can just put in desmos.com. That should come up. That's a free graphing utility, real great for algebra. You can also use it in calculus as well for curve sketching and so forth. CalcPlot 3D is great for three-dimensional things that you do in Calculus 3, but you can also use it in Calc 2. I only used it in Calc 3, but if you're taking Calc 2 and doing volumes of solids of revolutions and stuff, yeah, you can totally use CalcPlot 3D. It kind of gives you a better feeling for the three-dimensional stuff that you can do in those classes. Also recommend study groups. Again, you may want to check with your instructor. Just because, if there's an element, if your instructor's a little bit strict on rules as far as cheating or copying, doing work together, just make sure you ask them those questions at the get-go of the term or your class. Just make sure it's okay with them. But if they're cool with it, I totally recommend study groups. I've benefited a lot from study groups and study buddies. Also recommend tutoring. Now, of course, I'm a tutor, but I have actually received many hours of tutoring for math. It's very helpful, and it doesn't mean that you're not smart. It doesn't mean you should know all this because you shouldn't. You're a student, and going to tutoring is just one step in the right direction of becoming a better student. Just learning, and in learning is something you do for life. So you're always going to be learning new stuff. So I would totally recommend going to a tutor, whether it's a peer tutor or even a professor who's offering tutoring hours. However it works out, I definitely recommend going to tutoring. If you need it, or even if you don't, even if you get it, but you just want some input, some feedback, it's very helpful. All right, so let's just get into it here. We've got algebra, and yes, it is kind of a balancing act. This is by way of summary mostly. I'm going to assume most of you know what I'm going to be talking about in algebra, so I may go a little bit quick here. All right, so just kind of for a review, let's keep in mind some mathematical terminology. Over here on the left, I've got a few things. Now, some of these things right here, this is kind of from arithmetic, and we don't use we're not going to be using these terms probably a lot. So I'm just going to kind of cover that up. And I'm going to talk about two things, terminology-wise, that I found are kind of good to get distinct. One is terms, and the other is products. So we talk about terms, we're talking addition. So if I say, what are the terms in this expression here? Well, it'd be A, B, and C. A, B, and C are the terms because they are being added together. Now, I could just as well probably put a subtraction sign in, since subtraction is just a special case of addition. So, when we think addition, subtraction, we're thinking terms, okay? When we do products, we're thinking multiplication. Now, those stars, those asterisks, those are really, those could be an X, those could be a dot. I'm trying to get across multiplication here. So A times B times C. So if I were to say, what are the products in this expression? Will be the A, B, and C. Okay, and that A, B, and C, those are just, as we say, dummy variables. They're just placeholders. Those could be numbers. Those could be polynomials. Those could be, an X, a common variable. I'm just using A, B, and C as a placeholder there. A couple of other things in the terminology it's kind of interesting is power, an exponent. A lot of times we'll sometimes call we'll say, 5 to the third power. Well, we can say that, but actually the whole thing is the power. So the 3 is not the power, the 3 is the exponent, as you can see here, and the 5 is the base. And again, we could put an x in place of that 5 and have, x to the third, or x cubed, or x to the third power. Several ways we could say that. And again, some more terminology down here. So when we also wanted to talk about sign numbers, I'm not going to go through all these because, again, I'm going to assume you've already had this in your algebra in high school. So just keep it in mind, and you really want to have these operations of sign numbers memorized. You don't have to memorize them exactly how I have them here. This is just something that I used when I was taking math in high school. Same with operation of powers. This is really important when we get to something called integration in Calc 1. A lot of times we use operations with powers when we do integration. And again, with sign numbers, the reason why I bring this up, I didn't say it earlier, is just so many mistakes I made in math were sign errors. Excuse me, just sign errors. So you do a whole page of math and then you realize I'm not getting the right answer. Well, it's all because in the second line or first line you messed up a plus or a minus. So just very important. Again, by way of review, the difference between a relation and a function, and domain and range. Again, here I use the same ones, just kind of interesting. Function, remember, that's kind of a special case of a relation. Function has distinct pairs with different first coordinates. So as we can see, each of these are distinct and each first term is different. Or excuse me, not term, first coordinate is different. The domain is a set of first coordinates, and they're usually the x-coordinates. So that's when we talk about the domain, that in this case would be the 0, 1, and 4. And the range is the second, so it would be the 2, 3, and 5, usually the y-coordinates. Again, for review function notation, we have f of x and we have y. f of x is the same as saying y usually when we're talking functions or equations. So they're equivalent in that case. And you can kind of ignore the 2x. I just threw that in there to show that these two would be equal, but really what I'm getting at is the f of x and the y are the same notation on that left-hand side. And then we have the 5 ways to view functions as an ordered pair. There's a graph with a vertical line test, rule, which is basically this over here, is a formula and equation. And then the mapping, that's that thing in, back in Algebra 2 or whenever, where they showed you, if you had a group of a little oval shaped or rectangle, and you had a group of numbers on one left-hand side and a group of numbers on the right, and we drew a line in between, that's what the mapping is. Function machine, you put something in, you get something else out. And the function is what operates on the input and output. So this is a little review from Algebra 2 or college algebra. Okay, 2 other things, kind of some terminology you get a lot of in Calc 1 that's kind of nice to just have a refresher on, is polynomial. Again, that could be an expression, equation, or a function. But it means, many names, comes from the Latin, many names, or we can think powers. So you're basically getting more than 2 algebraic terms that contain different powers of the same variable. So over here, this is an example of just polynomial exercises, or exercises with polynomials, and from a college algebra textbook. And you can see just some examples there. And the way they look, we can see they're all got, some of them have different powers, x to the third, 8x squared, 11x, and then here's just a number, -20, so forth. So rational expression, or rational, the word, and then we have, that could be just an expression with no equal sign. It could be equation with an equal sign, or it could be a function, an f of x, like down here. So here we're going to think ratio or fraction. Okay, so a ratio of polynomials, and then denominator cannot equal 0. So here's just an example of one. All right, and a lot of times though we would need to put a condition on it, like we would have a comma, and then we'd say x cannot equal -2 or 2, because if it did, then we'd get, 2 squared is 4, -2 squared is 4, 4 minus 4 is 0, and we can't have a 0 on the bottom, as you well know from your rules back in algebra. Another thing just to keep in mind is exponential and logarithmic expressions and functions. And my big quote there is just from my algebra teacher, and it was, a logarithm is an exponent. I don't know if that was original by him or not. Probably wasn't, but that's what the quote is, and also this blackboard thing here just kind of demonstrating that. And that's one way you can kind of keep the interchange between exponential and logarithmic straight. Just a little nugget of wisdom there that or of knowledge there that kind of helps that interchange between the two. And here I have them graphed just so you can see them, and you remember they're kind of like inverses of each other. Here's a summary of log rules. Those will be important. Kind of as an example, I have the RC time constant, and physics 2 is an application of logarithmic behavior, where we actually have to it's not too important to know what the RC time constant is. It's something that deals with when you have a switch on a circuit board and the charging and discharging of the electricity through it. We get this thing called the RC time constant, and one of the things we have to use on it is some of these log rules, or are some of these log rules. So it's just something that keeps popping up again and again, and it'll come up in Trig, it'll come up in Calc 1, it'll come up again in Calc 2, and yes, you'll have logarithms in Calc 3 as well. Just not too hard, but they'll just keep popping up here and there. Okay, piecewise functions and inequality versus interval notation. I'll start with the piecewise functions over here on the right. This is just a good concept to have of breaking down a function and graphing the parts that are given. Like in this case, we have f of x equals -x plus 1, and then we have some conditions given. We also have equals 2, and we also have x squared. So we're basically given 3 functions, right, in one. And notice though we're given conditions, boundaries on it, boundary conditions. So when this is how it would be graphed in your calculator. You'd have to do each one separately. That's what this is showing. These different lines, and then here's just a point. But then when we put it all together, if we were to hand graph it, this is what it would look like. And that's most likely how your instructor would probably ask for it. And you can see the shaded areas. And you can see the boundary conditions, because open circles, closed circles, etc. This is important in calculus because a lot of times when we do curve sketching, there are bounds. So this kind of analysis is used a lot in Calc 1. Over here, this is a lot of information. You don't really have to worry about all of it. Main thing I'm trying to point out is just it's good to review your open circles and darkened circles, closed circles. That means that the number that this is on, on the number line, if it's open, it means it's not included. If it's closed, it means it's included. And the same comes over into interval notation, and that is where you have a bracket, a parenthesis. A parenthesis means is equivalent to open circle, and a bracket is equivalent to closed. So you can actually put, if I wanted, I could put a parenthesis here on the number line, and here I could put a bracket, and it would mean the same thing. So you might see that in calculus, and again, you may not. They might just keep it in inequality notation. Just something to be aware of. Graphing. I'm not going to do any graphs for you here. This is just an example of how we would summarize some transformations in algebra, but you'll have transformations for trigonometric functions. So you'll get, again, trigonometry, and some of the stuff I already mentioned at the beginning, but there are a few things in technology, like your calculator, Desmos.com, CalcPlot3D. These are things that you can use to check your work. Sometimes your professor might say right from the beginning, we're only going to use technology, but it's always good to know how to do this stuff by hand, and that's where these transformations come in. Very important to know how to sketch by hand, which is kind of why my pencil's a little bigger than my computer monitor. That's just a little plug there for hand sketching. And yeah, it doesn't have to be perfect when you hand sketch, but it's good to kind of know how to do it, because if you don't know how to even do it by hand and you're just trying to check yourself with technology all the time, it can get overwhelming. But if you kind of know how to break it down into smaller chunks and do it by hand, then it makes it a lot easier just to check your work with, technology. So, one other thing to be aware of, as far as going forward in your math career, is just word problems are a thing of life from this point on, and it's important to know how to translate the English into math at an early level. Now over here I just have a few examples of how we kind of can do that with some word problem setups. These are common Algebra 2, college algebra, maybe pre-calc algebra type problems over here, but you're going to see word problems come up in trigonometry, and they're going to come up in calculus for sure. And I had in parentheses science courses. Yes, they're going to come up a lot in science as well, getting that English into math. So conic sections. This was a little video I have, and it may play here. And it's just to show, I'm going to keep it muted, but this just shows how the conic sections, kind of where we get the shapes from. I'll play the circle, just kind of review. So we split that cone, look at it straight down, and we get that circle. And we just keep cutting at different angles. Get an oval, but that's really, in this case, an ellipse. And I'm going to just speed this up slightly, because I think you get the point. Cut, we get that ellipse. Cut again, we're going to get that parabola. Last, remember it? Hyperbola. There we go. So there's your conic sections. Righty. So just a few applications of the conic sections. you can pause the video and read them all here. Hopefully it's clear enough on your screen. But I'm going to just talk about a couple of them that I found interesting. One is just the fact that you can use satellite dishes or parabolic microphones and stuff to hear like somebody over your neighbor basically over eating dinner, which I don't recommend doing that. But you can get these really cool reflections through a parabola, and it's just incredible some of the applications that can be used with the focus to, you know, for, I mean, satellites, for crying out loud. I mean, a satellite's out in space, but, you know, it comes right down into your everyday life and into your backyard or on your rooftop if you use a satellite dish. It's just really neat, some of these applications. Whispering galleries. Now this one, I just put a picture because I didn't really know at first what that is. So this is basically where you can, because of these, you can see these arches and then also this kind of oval shape here at the top. You can basically speak in different areas of this cathedral in this case. And yeah, the sound is going to echo, not really echo, but it's going to carry along the lines kind of through the focus. Here's an ellipse kind of shape. And you'll basically be able to hear somebody's voice clear across the room. And as you can see, this is a very, very large room. So that's just kind of a neat one. Definitely going to touch on orbits of planets in physics. Oh, here's a good note. 1D. Okay, yeah. Path of a projectile without air resistance. Okay, so that's like throwing a baseball or a football. That might be a better example. Just throwing a football through the air. You're going to get parabolic. You're going to get parabolic motion through that. It's going to kind of sketch out that shape of, you know, this kind of shape. So that's something that's kind of a fun problem because you can do it in algebra. You can do it in trig. They're a little bit optional at that level, but you can revisit the problem in Calc 3 without air resistance. That's what this note is about. And that's kind of fun to do because you kind of get an appreciation of where we get the simplified version in algebra without the calculus. And of course, once you add air resistance, it's not necessarily a perfect parabola, but it's just a neat application. And then hyperbola, there's some neat things. It's a little bit less common, but you do get some things here. We get the long-range navigation, and here's a image of that. And then also, apparently I have a note here about hyperbolic paths arise in Einstein's theory of relativity. Very cool if you're going to go on to study astrophysics. Okay, so that question I had at the beginning, ever wonder if all the algebra you took in high school and are taking again in college is worth it? Let's take a look. Okay, this is just a Calc 2 problem with volume. That's why we have a V on the left-hand side, is we're basically trying to get a volume. So interesting enough, just kind of draw a box here. This step, we have this little symbol, okay, that little squiggly kind of looks like an elongated S. That's an integral symbol. Okay, that integral symbol is indicating that this is the only step that is calculus. The rest of the problem is arithmetic and algebra. I just said that backwards from my slide. Sorry about that. But all this is just simplifying algebra, okay? Even this step that is calculus, what we do in it is basically algebra, okay? It's basically what I was saying earlier about powers. You're using the operations of powers, okay? And then you're just simplifying. And look at all this. We got fractions. We don't have decimals or crazy things like that. It's just fractions. Okay, so that's like arithmetic from there down. So yes, it's totally worth it. And it's definitely, here's the thing, if you didn't learn algebra in algebra when you took it, whether it was pre-calculus or college algebra or high school, you will definitely learn your algebra when you take trig and when you take calculus. Okay, so it's kind of a funny thing. You really actually learn the algebra when you're taking the higher level maths. Okay, yep. All right, trigonometry. Alrighty, so yes, I do have a pun there, but it is usually based off right triangle trig. So as a way of review, right triangle trig, that is where we have a triangle with, right angle in it. Kind of basic, but that's where we get the sine, cosine, and tangent, and then I have some of these things. You may have learned this mnemonic device, SOHCAHTOA, in grade school maybe, and that's, or middle school, high school, somewhere in there. And here this dashed line kind of represents a fraction line where I have quotes over. So sine is our opposite over hypotenuse, cosine is our adjacent over hypotenuse, and tangent is our opposite over adjacent. Okay? And again, if you need a refresher on some of the stuff, pull up another video on YouTube and I'm sure you can find it. All right, so this is all based off the unit circle. We talk about that in trig. So again, I'm gonna kind of back off a little bit of review and talk a little bit more to people, because I'm sure there's some of you out there that are going to be taking trig soon. So I'm just gonna kind of slow it down a little bit here and just kind of explain that this kind of interesting looking thing here is sort of the basis of what we use the trig, where we get the trig functions. And you go, how do we get that off a circle? And what are all these numbers? Okay, let's not worry about all these numbers and stuff right now. It's another way of measurement, okay? Here are degrees, and then we have these things with pies. That's called radian, okay? And these things are ordered pairs, yeah, kind of like x and y. But interesting enough, instead of x and y, that can be cosine and sine. But that sounds a little strange. But you'll learn that when you take your trig course, and that's one of the reasons why they have those here, is that you can kind of remember sine and cosine based off the ordered pairs. So let's imagine if I just kind of inscribed a triangle here. I'm going to inscribe right triangles, show the correlation between the unit circle, that's what this circle is, and the Pythagorean theorem. Okay, so here's an inscribed right triangle. Okay, and notice I'm taking it to these special points, and you'll learn, you'll basically have to kind of memorize this circle. Very important. Should have said that earlier, that you will memorize the unit circle when you get to trig. So I'm going to inscribe a triangle to the special point here. I'm going to do it to the next one, and I'm going to do it to the next. Notice that those are right triangles, each of those. Okay, we got right angle on each of them. And notice I could do SOHCAHTOA on each of them. I could do sine, cosine, and tangent. And that each one is going to have a radius of 1 in this case. And say, how is it 1? Well, this is also kind of where we get that kind of the proof of the Pythagorean theorem as well. We're going to get that hypotenuse here. And I won't go into detail, but that is basically, if we were to do sine and cosine, that's where we're going to get these numbers here in the ordered pairs. And I'm going to leave it to your trig instructor to kind of go through this, and maybe they won't, I don't know if they'll necessarily explain it this way, but this is a really cool thing that just I wanted to kind of mention, because it really shows the correlation, as I said here, between trig and the unit circle, and why trig functions are called circular functions. So here's a little mnemonic device for recalling which trig functions are positive. Now I know I didn't talk about that before, but you'll learn in trig that certain functions are positive and other ones are negative. You say, well, how do I keep them straight? Okay, well, we always measure, okay, counterclockwise from the positive x-axis, meaning we always start here. I should have drawn this further down, but we always start here and go around 360 degrees to here. Okay, so this one's just blank, this circle. Same thing as this, but I'm just leaving it blank. So what we do is we're just going to say, well, let's just remember the ones that are positive. So all of them are positive in quadrant 1. Okay, these are quadrants 1, 2, 3, and 4. Okay, S for sine. Only the sine is positive in this one. By default, all the other three are, the other two. And then we can also remember the reciprocal functions as well, like those would be negative. So let me back up, sorry. So all are positive, sine is positive, tangent is positive, and cosine is positive. So in each respective quadrant. So all in quadrant 1, sine in quadrant 2, tangent in quadrant 3, cosine in quadrant 4. By default, all the others are negative. Okay, so you can kind of remember that. Again, going counterclockwise, you can remember it. All students take calculus, all teachers state college, something like that. You can make up one. And this is also going to be important in physics, physics 1, because you do some things where you measure with angles. So this is kind of a neat thing to remember. Again, getting back to circular functions, like I was saying, remember those inscribed right triangles. Here's that radian measure. I won't go into detail about that right now, but you can see where it's related to a circle. Here's our trig functions, and I want you to notice that on the peak, I'm going to talk about the sign right here. On this peak here, if I cut this little hump, this little mountain off, and I slid that little mountain over here, over this trough or valley. Okay, we're talking mountains and valleys. So let's say I cut the little mountaintop off, slid it over here, over this valley. Notice it would kind of make a circle. And that is deliberate, okay? That's interesting. All right, so now we've got a circle. That kind of goes back to our unit circle over here. So that's why we kind of call these things circular functions, is they all are based off the unit circle. And notice they make this wavy pattern, but that wavy pattern is again related to kind of a circular function, or circular motion, and sometimes this is called oscillating motion. Notice it's going up and down like a wave. Okay, now that little box I just dropped there, that was damped because it eventually stopped. So it's damped motion. But that is actually the same type of motion that is used in springs, and it's also used in noise cancellation technology. Another term for it sometimes is harmonic motion, as harmonic functions. These can be called oscillating functions, circular oscillating functions, harmonic functions. And they can be used in noise cancellation technology because sometimes, now this is very, very simplified what I'm going to say here, but imagine you had a sound, imagine this was describing sound and you had a wave. Let's say that's background noise. Well, what if I did this opposite and did a wave going this way, then cutting down, and then coming back up and cutting down? That wave would basically cancel out this wave, and then essentially you wouldn't hear it. So it's kind of a neat application. All right, trig functions. So we basically have these: sine, cosine, and tangent. Sine, cosine, tangent. You say, well, what are these? Cosecant, secant, and cotangent. You may have had that maybe back in middle school or high school. Well, those are the reciprocal functions. So it's basically a reciprocal. It's 1 over that, so flip-flopped. So those are the 6 key ones. And then we have our inverses. So a lot of times it's kind of hard to get, we can kind of get confused between reciprocal versus inverse, but there is a difference. And you can see that in the graphs, okay? That's the reason why I'm bringing these graphs up. Just a little bit of a, again, sneak peek. I won't talk anymore about it. All right, moving on. Other topics covered in trigonometry. Trig identities, law of sines, law of cosines, solutions of triangles, complex numbers, vector algebra, polar coordinates, and parametric equations. This stuff down here at the bottom, some of that you should have in preparation for calculus, but a lot of it's going to be just in preparation of calculus. The trig heavy stuff is definitely going to be the stuff here more at the top 3. Here are a few application problems of trigonometry. Static equilibrium. So for example, this question is asking, what is the tension of the 2 cables? That's kind of important. You know, we want to figure out the tension, and then you say, well, why would we want to know that? Well, in a physics problem, they might ask you something else, saying, you know, what would be the max weight you could put on there before one of those snaps? Okay, and then which one would snap first, etc. As you can see, that'd be a really cool design application. So if you're in engineering or something, you can definitely see how this would be applied. Again, there's another problem. This one, though, is a little different. This one's kind of asking where, it's basically asking what is the height of the cable at a point 50 feet from the center of the bridge. So based on all this, you know, all these measurements and stuff, you can actually use trig and algebra and figure out exactly how high that thing is above this bridge at that point, or right here above that point. So just different application problems. These are very similar to physics problems, so you're going to see these in physics 1 problems if you're going to take physics. Something else to keep in mind is the dot product and cross product. I am not going to go through how to do these. There's some great videos out there though on how to, but these are things that are going to surface again and again, mostly in Trig, and I would say Calc 3, and then if we're going to include science, Physics 1 and 2 both use it, so you'll see it in Physics 1 too. But yeah, it's really not until Calc 3 that this kind of picks back up again. Calc 1, it's not quite as important to know these, but if you're going to continue with your math or you're going to be taking physics, definitely something you might want to invest some time learning about. Yes, I know. All right, let's go on. Examples of various trig problems. So here's just a smattering of some of my homework from when I did trig. Here's an example of the tip to tail method of adding or multiplying vectors. I think this, yeah, in this case it's just addition and subtraction of vectors, how we can draw them out. Vectors have both magnitude and direction. So magnitude meaning that like a length. So a certain, if we say like this one here is, W, it's this long that's green. Here's V, but when I put them together, notice it's the length of W and V put together in this one. There's a few different methods you can do it. You can do it physically like this, or like kind of by a picture, but then you can also use certain rules to analytically add and multiply them. Trig identities. This is just an example. This is actually kind of a long, not to scare you guys, but this is kind of a long one of how basically I'm giving something over here, looks nothing like the thing over on the right hand side. But I can do all this manipulation using some rules that they'll give you in trig and basically come out to something that's equivalent. Notice here, now trick to these is you don't cross the line. You don't really want to go, you don't want to be solving them on both sides. I manipulate just a little bit, like three lines here, 1, 2, 3, to get this. But notice that is identical to what I finally ended up with on the left-hand side. And that's trig identities. They can be kind of tedious like that, but they are kind of fun. They're sort of like solving puzzles. Here's an example of polar conversion from Cartesian or rectangular. That's like, x and y. We can go from x and y to r's and thetas. That's what this is right here, x and y to r and thetas. You'll learn about that in trig, but it just gives you an idea of the polar grid. And again, how that kind of goes back to our unit circle. Notice it's circular. Alrighty. Calculus. So yes, this is definitely it feels like a gauntlet when you go through calculus, but it is definitely worth it. So calculus, you're going, okay, there's 3 of them. Yeah, so what's the difference? Okay, so you can pause the video here and read them all if you want to read that, what's all written down there. But, okay, here are my short answers, right? So my short answers are basically the credit hour difference. Okay, so Calc 1 is 5 credit hours. Everything is completely new, but it goes hand in hand with Physics 1 if you're having to take that, or if you want to take calculus before Physics 1, however you want to work that. Calc 2, same, 5 credit hours. You get some exposure to 3D graphs and drawing of volumes. Integration on steroids, and that's kind of meant to be funny, but yeah, it'll kind of feel on steroids. Now integration, you're going, what's that? If you haven't had calculus, integration is just a process. It's like an operation. So I'll talk a little bit more about later, but it's like, when you were back in grade school, you learned you learned how to add and subtract and multiply and divide, but then you learned powers. You learned how to multiply something to an exponent and learned how to add them and subtract them. It's a new operation. Okay, it's kind of like that with integration. It's learning new rules, but you're going to learn a lot of different ways to apply it in Calc 2. Operations and nomenclature are somewhat familiar, but lots of new formulas and problem solving techniques. I basically just said that. I should have just read my slide. Problems are more tedious, and that is true. Calc 2, they're going to be a little more tedious. They're going to take more time to kind of learn the pattern on how to get them down. I mean, Calc 1 can take a long time too, but you can kind of somewhat wing it on Calc 1. Calc 2, there's going to be some problems where you kind of have to learn a method for solving things, and it can be your own way of learning how to remember those steps. That can be yours, but you're going to have to make sure you're doing it right, because the problems can get tedious and you can make a small mistake and the whole problem will be wrong from there on. Calc 3, oh, here's the difference, big one. It's 4 credit hours at SPC. Okay, and that does make a difference. So you feel a little bit less pressure. Everything in it, there are some new things, new theorems to learn, but most of the operations and nomenclature have been at least introduced in previous math courses. So it's not going to be like, oh, I've never seen this stuff before. It'll be somewhat familiar. So my oversimplified description is that Calc 3 is basically like trigonometry and calculus 1 in 3D space. So instead of just an X and a Y, up, down, left, right, we get X, Y, and Z. So we get to go up, down, left, right, and we also get to go forward and backward, or however we say that, fore and aft. So we're working in three-dimensional space now. And Calc 3 goes hand in hand with Physics 1 and Physics 2. So as it turned out, a lot of people take Calc 1 with Physics 1, Calc 2 with Physics 2. I actually kind of was out of sync with that a little bit, and I took Calc 3 when I was taking Physics 1. And then I took DE, which is another class called math class, differential equations. I took that when I was taking Physics 2. Reason why I say all that is just basically when I got to Calc 3, it actually was kind of cool because I wasn't trying to struggle and learn Physics 1 and Calc 1 at the same time. I had already kind of learned the calculus behind it, and I kind of was familiar with it. And so when I got to Physics 1 and 2, when I was already in Calc 3, it kind of made the physics a little more meaningful when I did it, and vice versa, made the calculus more meaningful as well. So just kind of a personal note there. Okay, so derivative notation and curve sketching. Curve sketching, this is kind of an example of curve that was hand sketched. Yeah, and that's something that you spend, I don't know, maybe the second test. For me, it was my second test in Calc 1. You spend some time doing curve sketching. So you go, what is curve sketching? Okay, so in calculus, we're interested in the existence and behavior of a curve's slope at a point, okay? So notice here, I've got little points. Here's a little sharp dip, comes back up to a peak, kind of comes down, kind of flattens out here. That's why there's this little bar, little tangent bar here. Goes downhill, going to ski really fast, hit the bottom, and then we're going to have to hike back up the mountain, up to the maximum, and then back down. And that's what these points are. You'll learn special terminology. You probably know some of these from algebra. Here's a minimum and a maximum. But you're going to learn some other terms too, like flex points, cusps. That's that really sharp corner. Or here's one called a corner. Okay. So there's some different things. And you go, why are we concerned about that? Well, we're interested in slope. And if you recall what slope is, it's a change over something over a change over something else. So a lot of times it's a change in x, which is, or excuse me, a change in y, I spoke, over a change in x. So that's that rise over run, or that how fast are we increasing or decreasing? How fast are we going up? How fast are we going down? Okay, and so that's what this is, calculus, especially Calc 1, is all about, is we're just interested in, is that rate of change, how is that rate of change happening? Is it going up? Is it going down? Another question is, does it exist? Like at these really sharp points, we're asking, can you get a rate of change at these points? Anyway, that's kind of brief overview of curve sketching. But then as far as notation goes, here we have our first derivative and second derivative. You can kind of ignore the second derivative. I just kind of put it there for good measure, but I'll just show you the first one for now. We have y prime, and you go, well, what are these doing all standing by alone? Well, imagine if we had an equal sign after each one, okay? Y prime equals, and then you have like, I'm just going to throw something out again, 2x, okay? So that's just how it would be written completely. if you had taken a derivative. You would have a parent, you'd have a beginning function up here, and if you took the derivative of it, you'd get y prime notation, or you could have f prime of x, you could have dy dx, you could have d over dx with the bracket symbol of the function, and you go, what is f of x? Well, that would refer to what was up here. You would have f of x equals, and then your next line would be this equals, and then you would have already taken your derivative, which again is a new operation. And here's another form that we can use as well. Okay, so the derivative it's a rate of change, and it can be described in relation of the size of like the price of a pizza to the size of the pizza. It could be, the rate of change of a bacteria growth in a Petri dish, how fast is this population growing? There's lots of applications for the derivative, very many. I'm not going to play this video because I cannot, on the program I'm using to record this, I can't share audio of the video, so I'll leave that for you guys. The source for it's the mechanical universe. I'll go ahead and tell you that. It's the mechanical universe, the episode called Law of Falling Bodies, but I'll also have, and that sounds kind of weird, but that's Law of Falling Bodies, meaning Galileo's law, which eventually kind of led to Newton, Isaac Newton, to get to acceleration due to gravity. So we drop a ball, it goes down. That's what that means when I said law of falling bodies. So yeah, you can watch the video between the times listed here, 18 minutes, 18 seconds to 21 minutes and 36 seconds. And there's a really good little practical application video here on this. I'll also have the sources all linked as well. And let me go on. Oh, there it is. Yeah, you can see what it looks like on YouTube. There it is. So integration notation, this again is a new operation. So an idea is like getting back to that piecewise function or a boundary. If I have a and b on the x-axis horizontally, I want to go between a and b. But I want to find the area underneath this line. Well, how do I do that using like algebra, up through algebra? Well, I could put a bunch of rectangles under there. Cool. Okay, so that's an approximation of it. It's not exact, though. But what if I made the rectangle smaller? See these white gaps we have? That's like our extra space. If I made the rectangles skinnier, oh, then I can fit more in, and I have less of that white gap space. Well, imagine if I could do that infinitely, like really, really skinny, like super skinny to infinity. Okay, this is what I would get, a smooth looking area, right? So now I've found the area under the curve, but between a and b on the x. So I've located what I want. That's the idea of an integral, is it's a summing up. That's why it's a little skinny s. That's what that is. Actually, it comes from sum in Latin, or something meaning to add up in Latin. So that's why we have this skinny little shaped symbol. And it's saying we're going to sum up everything under here until to a certain, to infinity almost, and then we're going to get this smooth area, all of it. And so that's really useful because now we can find areas underneath kind of funny shapes that we couldn't do before. And you're like, well, why do we always want to find areas of stuff? Well, we can think of areas like the area of cloth needed to make a pillow or something like that. But area can also be applied to a lot of other things in science and in nature that we can apply it to. So it doesn't necessarily mean the area represents like a flat surface of space. It could represent something totally different, like a population. It could be a concentration of a solution, depending on what you're doing, how you're applying it. It just has a lot of different applications as you go further into your science courses. You'll begin to see it. Again, here's another video. I have a note here to play from 16 minutes 32 seconds to 17 minutes 20 seconds. and 19 minutes to 51 seconds and 20 minutes to 57. Hopefully you can read all this on the recording, and I didn't need to say all that. But here's this one. This is the mechanical universe. Again, it's mechanical universe, and it's uploaded by Caltech. Okay, and you can see it's episode 7, integration. So that video segment also shows how derivatives and integrals are inverses of each other. So the derivative and integral basically undo each other because they're inverses. So just kind of as a quick example, this blue line here is going to represent that d sub x. That means derivative. That's just for now. And then here we have, it's very light, I apologize for that, but here we have a little integral symbol in red with a little dx. That's going to be our integration. So if I took the derivative of sine, that's what this is. It's going to be a trig function. If I took the derivative of sine, follow the blue arrow, I get cosine. But what if I wanted to take the integral of cosine? Well, I'd follow the red arrow. Excuse me, I apologize. So I'd follow the red arrow, and that would take me back to sine. So without even knowing calculus, if you haven't taken it, you can clearly see that if I were to take a sine, follow the blue arrow, I get a cosine, but then I was going to integrate it, I go right back to the sine. You can see that they just undid each other, that they're inverses. Kind of a neat visual there. All right, here again is another kind of scary sheet, but this isn't to scare you really. It's just to kind of show that these are rules that you'll learn for derivatives and integrals for Calc 1. This is something you learn in Calc 1. And there's a lot here. Now your instructor may let you use a cheat sheet kind of like this, and may even let you add to it like my instructor did, or they may, or he or she may say, no, you can memorize all those for the exam. Or they might be kind enough to tell you there will be, so many out of these that you'll need on an exam to memorize. Here's just another application, just decided to throw it in here, an application of hyperbolic cosine that can be seen in the catenary shape of bridges. That's the shape. Here's one kind of going down, and then here's one inverted where it's up. So that's just kind of a neat application of hyperbolic cosine. And you go, what's hyperbolic? That's something that they talk about in Calc 1, kind of towards the end. Okay, here's a Calc 2 example. Again, these are kind of like applications. There's a couple different dishwasher method and shell method, and these are methods for finding the volume of like a little solid thing. And I don't know if you can envision this or not. If you've already taken Calc 2, you probably can, but if you haven't, this might look a little strange. But here I have something that looks like the upper half of a parabola, just this line, okay? Just look at that line on where my cursor is. Okay, so I was given that. That's what this is, and that actually should look familiar from algebra. We've got that square root and then x plus 1, okay? And notice they gave me a 1 and a 4, so that means from 1 to 4 on the x-axis, that's again a boundary, piecewise function again. Okay, those boundaries. So then we got this curve. Now go ahead, I usually, instead of just drawing it here to 1 to 4, I usually draw the whole thing as far as I want. But then I remember to shade in only from 1 to 4, okay, because that's all we're going to be using. Notice that kind of looks like that area under the curve that I just talked about with integration. So that's what we did. But then they also give us some other information here, and you can basically, you map that, but then what they're asking for, and I may, I don't have the original question in front of me, but what they're asking for is they give some sort of bound here. And what I do is I would sketch this little dark rectangle in there. But what I'm going to do is I'm going to sweep it out, and imagine I could spin that around. I tried to draw it sort of 3D, so you could see, imagine if I swooped that down kind of like a pinwheel, sort of like dropped this down and just swooped it around. It would sweep out this kind of shape that looks like a disc. And then what we essentially found by the time we're done is the volume of that little disc. And you can do that for different things. And I won't go through each of these, and that was kind of a lot. You're saying that's a lot for just finding the volume of a disc, but it's a neat application because it allows you to now find volumes of things that aren't just cubes or a sphere or a perfect geometric shape. It allows you to find volume of things that you find all the time in manufacturing, design, etc. All right, so that's mostly the close to my calculus. I didn't really get into Calc 3 or differential equations or statistics, okay? I kind of left those hanging, but I'm gonna, if you're interested about those, let me know, and I'll try to maybe make another video on talking about those at some point. But here's a few additional STEM math courses at the 2000 level that SPC offers. Okay, we have differential equations. That's kind of the natural one for those of us that are engineering majors. And my plan is to do mechanical engineering. So a lot of times we have to do all calculus, so 1, 2, and 3, and then a lot of times we have to do DE, differential equations. But again, for people that are not engineering majors or math majors, they don't necessarily need to take those all the time. So they might opt to say, well, I can take statistics instead of, whatever it might be, Calc 2 or something like that. I don't really know all the STEM majors, so I'm just kind of being hypothetical here. But if you do have an opportunity to take statistics, I'd highly recommend that. I have not taken this class yet. I would like to take statistics at some point. But here's a few of the different course offerings that SPC has, and a little description along with the differential equations. Just wanted to mention those. Just on a final note, just kind of an interesting little graph I found in actually an economics textbook. But it's kind of cool. It's like, what is your math worth in the market? Well, kind of as you go up the line here, you kind of see, well, here's the mathematics. So I don't know if that includes, actuary or not. I'm assuming probably does. Maybe also education. I don't know. Probably not education though. I don't know. I really didn't study this too thoroughly. But anyway, as you go up here, you can kind of see that, the more you're applying math in your career, there seems to be a greater increase in both your starting salary and increase by mid-career. So that's kind of an encouraging thing. So keep at it, even though they can be challenging, frustrating at times, but definitely going to be well worth the investment. And they're great. STEM math courses are just so great at teaching problem solving and analytical reasoning. Whether you end up using all the math in it or not, they're great problem solving. Really get you introduced to that kind of concept of analyzing a problem and solving it, and then kind of understanding the backstory behind it as you continue to go on in your math field. So here's just some references. I think they're all they're all on one slide here. Here's some references. You can pause it. I'll try to have those uploaded underneath this video as well, so you can just get directly to those hyperlinks. So the videos should all be hopefully working, or at least you can copy and paste them. So thank you guys so much for watching this. If you watched all the way through, I appreciate it. And if you didn't, I'm glad you skipped around and maybe got to this point. But thank you guys so much for being amazing students, and keep at it with your math. And you have a great rest of your school year.